Hello and welcome to day two of the 2025 AMS Weather Band Jamposium. Yesterday we had three fantastic and engaging sessions. Today we will have three more where experts within our community will share their knowledge and expertise. This year's topics were chosen by our Weather Band members, your audience here, based on your interest in our webinars and digital content throughout the year. We want this to be an interactive experience, so please use the Q&A feature that you see on the right to engage with the panelists during their presentations and continue these discussions on the Weather Band Forum. Thank you.
Yes, thank you very much, Marissa. So again, welcome and hello, everyone. Welcome to AMS Weather Band's latest webinar, the first one of our second day of the 2025 AMS Weather Band Jamposium. This one is Riding Tropical Winds and Waves, How ENSO Shapes Our Winter Forecast, with Michelle LaRue, Nat Johnson, and our moderator, Brad Coleman. Now, before we begin today, I would like to address more specifically some of the guidelines that we have during our presentation. If you have a question during our webinar, please feel free to put those questions in the YouTube chat that Marissa mentioned earlier. Should be to the right of your viewing screen when you're on YouTube. The questions that go there will be addressed as appropriate. We may also have some time at the end of the presentation where we'll focus on the Q&A specifically. Additionally, all communications should be appropriate for a professional audience that includes individuals from diverse backgrounds. So please be inclusive and respectful in your interactions. And now with that being said, I would like to introduce today's moderator, Brad Coleman. Brad is an atmospheric scientist and currently the second past president of the AMS. He has enjoyed a long and diverse career in meteorology and its applications. He started a 38-year NOAA career as an undergraduate student trainee at the Portland, Oregon, go Sounders, River Forecast Center. Over his NOAA career, he spent some time as a weather forecaster, research meteorologist, and lab director. Dr. Coleman then moved into the private sector, becoming principal program manager and weather subject matter expert for Microsoft before moving to the Climate Corporation LLC, where he was the director of weather strategy. Brad is currently chair of the National Academies of Sciences Board on Atmospheric Sciences and Climate, or BASC. Thank you. With that, Brad, the floor is yours.
Super. Thank you very much, Gideon. We're all very pleased that you're here today. I personally am very excited about the subject matter this hour and what we're going to learn, to just be able to see and learn about how ENSO shapes our winter forecasts. Growing up a frustrated snow lover in Seattle, I could never get enough information about, and guesses, forecasts and guesses about what's going to happen this next winter season. Also, as I moved through my career, my time working in the area of global agriculture, I developed a greater appreciation for how a skillful subseasonal and seasonal forecast was really the holy grail. And finally, just sort of there's this simple scientific intrigue of trying to learn and understand how something going on thousands of miles away in the tropical Pacific Ocean can actually be the best predictor of winter weather across North America. For this hour, we're very fortunate to have two experts in this area of scientific research and application, Michelle and Nat, and I'll introduce both of them in just a minute. Our plan and how we're going to work through the hour is each presenter will have roughly 20 minutes. Michelle will be going first, and we will break in there and have a few questions, but trying to stay on schedule, kind of make sure that works out, and then we'll move on to Nat's presentation. Following Nat, we'll finish up the hour with additional questions and discussion as time allows. I'd like to now introduce both Michelle and Nat. In times of uncertainty, and I think we all understand what I mean there, the true measure of a scientist and a public servant is not just their expertise, but their unwavering commitment to the people and the planet they serve. So this morning, even more so than usual, it is an honor to me to be able to introduce two NOAA scientists whose work embodies that commitment. Michelle LaRue is a physical scientist at NOAA's Climate Prediction Center near Washington, D.C., where she has worked for 20 years. For the last 17 years, she has led the El Niño-Southern Oscillation, or ENSO team, which is responsible for regularly issuing NOAA updates on El Nino and La Nina. Michelle is also a lead coordinator, writer, and editor for the ENSO blog, which is hosted by NOAA on their climate.gov website. She enjoys using the blog to engage the science-interested public on ENSO and other climate topics. Also, she is currently the co-chair of the U.S. CLIVAR Predictability, Predictions, and Applications Interface, PPAI panel, and also serves on the U.S. CLIVAR Scientific Steering Committee. She has previously served as a U.S. expert on the task team on World Meteorological Organization's accredited ENSO information. Michelle performs applied research to improve knowledge and prediction of seasonal, subseasonal to seasonal climate variability, and is an author and co-author of over 50 journal articles. Our second speaker will be Nat Johnson, a meteorologist at the NOAA GFDL, or Geophysical Fluid Dynamics Laboratory, in Princeton, New Jersey. Since becoming a weather weenie, I can relate to that, Nat. At a young age, Nat has wanted to push the frontiers of weather and climate prediction. Now, as a research scientist, he tries to make this happen with research focusing on a subseasonal to seasonal climate variability, predictability, and prediction, especially in connection with the El Niño-Southern Oscillation, or ENSO. In addition to his research, which has resulted in more than 80 authored or co-authored journal articles, Nat has served as a member of the NOAA ENSO forecast team and has been a regular contributor to the NOAA climate.gov ENSO blog since 2017. Nat received his PhD in meteorology from Penn State University. Prior to settling in the Princeton area in 2014, he completed his postdoctoral research at the University of Hawaii and the University of California, San Diego Scripps Institute of Oceanography. So, two awesome experts, and I'm sure you're ready to move on and listen to them. So without further ado, I'll pass it on to Michelle.
All right, I think we're ready to go here. Can everyone see everything? All right. Haven't heard anything otherwise, so I'm going to go ahead and forge
Looks good,
ahead.
Michelle.
So, all right, great. Welcome to the El Nino Southern Oscillation update. As Brad mentioned, I'm a longtime veteran at the Climate Prediction Center. It is housed within the National Centers for Environmental Prediction, which is housed within the National Weather Service, which is part of the National Oceanic and Atmospheric Administration. And it truly is an honor to be here today talking to you all. Ultimately, in our jobs, we're really about the service. And I think that it's been the honor of my life to be able to be a scientist within NOAA and present information that is so essential for risk management and planning. I often get the question, you know, how does this work? Why are you guys so good? I mean, we are honestly internationally recognized for these ENSO products, and my response is the team, and the team are the folks that you see listed below. The strength of the team is in that everyone has different expertise and something to bring to the table, and we don't perfectly overlap. There's some folks on this team who are modelers, so they're creating the models that we use for our forecasts. There's others who are oceanographers, so they understand the wave motions. There's others who are more dynamicists of the atmosphere, and they bring that to the team. And we have statisticians. We really have it all. We also have some fantastic communicators. And the ones in asterisks, including Nat Johnson, who you'll hear from next, are with the NOAA climate.gov ENSO blog. And so twice a month, we update the ENSO blog with the latest and greatest on El Nino and La Nina information. So please check that out. All the figures in that blog are free to use. You're going to see a whole bunch in this presentation today, both from my talk and also Nat's talk. Keep in mind, you can find those on the blog and you can use them for your own stuff. So with that, I'll go ahead and forge ahead and just remind you all, I recognize that some are not as ENSO interested as others. But ENSO, which is my acronym for the El Niño-Southern Oscillation, has three different states. You can be in an El Niño, which we often define as above average temperatures at the surface in the central eastern equatorial Pacific Ocean. There's La Niña, which is below average sea surface temperatures. And then ENSO neutral, which tends to be closer to the average or normal sea surface temperatures across the tropical Pacific Ocean. All right, so we're really focused on the equatorial and tropical Pacific Ocean when we diagnose the state of ENSO. And as Brad mentioned, this has ramifications across the entire globe because the shifts in the rainfall and winds have knock-on effects. You can think of a domino sort of dropping across the whole globe. And the greatest part about ENSO is that we can often see it coming many months in advance. So when we see those indicators, we can then start hedging and doing our risk assessments and planning based on the possibility of El Nino, La Nina. I should also add, and these diagrams show it, is that it's not just a change in the sea surface temperatures. That tends to be our most important metric. And the reason it's important for us is because it is easier to see El Nino, La Nina in sea surface temperatures. There's also changes in the atmosphere right above, but those sometimes are a little harder to see. It's a little noisier. You can think of your day-to-day weather variability. It can be very chaotic. And so for that reason, we tend to emphasize these ocean indicators. So right now I'm showing two images. The top left is neutral, which is the more normal state. So if you were just kind of stroll down to the tropical Pacific and see what's going on, that's the image you would see. The bottom right there is La Nina, and I'm emphasizing that today because we are in La Nina conditions. And what you may notice when you compare the neutral and La Nina plots there is that La Nina looks very similar to the neutral condition, except it's just stronger. In other words, what we see is cooler waters in the eastern Pacific. We see warmer waters to the western Pacific. And as a result of this shift, we tend to have more rainfall and cloudiness and convection over Indonesia and the western Pacific. We see more sinking motion because it is cooler in the eastern Pacific. And this whole overturning circulation is called the Walker circulation. And that is essentially what touches off the impacts for the rest of the world. Okay, this is our ENSO alert system. We have advisories and watches, both for the warm state, El Nino, and the cool state, La Nina. A watch means that there's a potential for La Nina or El Nino to form in the next 6 months. An advisory means that it's here. And when you look at the latest NOAA CPC update, we are in a La Nina advisory. This is the update that is dated the 13th of February. We only update once a month on the second Thursday of each month. So the next update will be March 13th. So in this update, we said La Nina conditions are expected to persist in the near term, with a transition to ENSO neutral likely during March, April, May 2025. And we put a probability on that because these are climate outlooks, meaning that we don't know for certain. This is not like a next day weather forecast for temperature where you can be more certain. So usually in ENSO, you have less certainty. And so we put in those probabilities, like 66% chance. Here are the sea surface temperatures. Remember, I was saying La Nina is a cooler state in the tropical Pacific. So these blues you see there are below average temperatures. The reds are above average temperatures. And you're seeing an animation from December to last week where you see the ripples of this La Nina essentially shifting in the tropical Pacific. Now, this is pretty amazing. This took a huge effort from NOAA observing systems to create this image. I mean, we do not have the resources to have a thermometer at every square inch of the tropical Pacific Ocean. So how is this happening? Well, one is the satellite infrastructure. NOAA has all sorts of satellites up there that are helping monitor these changes in the ocean. But we can't just rely on satellite information. We also need to have immediate temperature readings at the surface. And for that, we have buoy systems, which NOAA maintains. They send out ships every now and then to maintain those buoys. And that helps calibrate the satellites so we know how intense this La Nina is. And this is a huge effort. I'm talking about agencies and hundreds of people who are involved in this effort just to get us to this image. So it really is valuable to have this infrastructure in place. So yesterday, I wanted to note something here. Yesterday, ENSO Forecast in Peru actually issued a coastal El Nino watch. All right. So what they are noticing is in the Eastern Pacific, in the last couple of weeks, we see a dramatic warming, and you'll see that right here. All right. And so that's a more local feature. Right now, we're looking more at the basin-wide feature that tends to impact North America, that shifts in the rainfall and all that. Those are the impacts that we focus on for North America. But for Peru and Ecuador and Western South America here is very important to watch these temperatures in the Eastern Pacific because this can touch off heavy rainfall and floodings in their regions. So that's something to keep an eye on. Okay, sorry, back up. I can take this box here, I can average the sea surface temperatures and look at a time series of this. And so I'm doing that with the black line here. This is 2024, now 2025. And I am also showing past La Niñas. These are the gray lines in this image. And so what you can see is that we dipped into a La Nina in December, and we're in definitely a weak event. It's on the warmer side of all these past La Ninas. So this is a very marginal event, which is what we've been expecting for several months. This is subsurface temperature. So not only do we want to look at the surface, we also want to look at the temperatures below the surface of the ocean. And why do we want to do that? Well, that's because this provides the fuel for El Nino and La Nina. We can often see months in advance changes in the subsurface ocean, which portend changes to the surface ocean. There's not a one-to-one relationship. As you can see in the Eastern Pacific, we have this shallow region of warmer temperatures. That's that potential coastal El Nino maybe. But in the subsurface, we still see a strong pool of below average temperatures, which is an indicator that La Nina will not be going away immediately, especially in the central and the east central Pacific. These are shifts in rainfall anomalies, all right? So I'm looking at a variable called outgoing long wave radiation, but really its value is that it gives us a proxy in the tropical Pacific for where we're seeing more and less rainfall. So whereas the oranges here, it's below average cloudiness and rainfall in the central Pacific. And right now we see above average cloudiness and rainfall over Indonesia. And this is a telltale sign of La Nina. We also have a time series here of this box. And what it shows is actually we're seeing quite strong signal of La Nina in the atmosphere. So this is definitely in the upper tier of La Niñas insofar as this rainfall pattern goes. This is looking at sea level pressure anomalies. And so as one can imagine, if you have more rising motion over Indonesia, more rainfall, that means at the surface you have lower pressures. And that's what we're seeing. In the Eastern Pacific, we're seeing higher sea level pressures. And when you take a time series, the difference of these two regions, you get the equatorial SOI. And this is one of the strongest positive values in the equatorial SOI, meaning that this is very strong when relative to other La Nina events. So from the ocean perspective, we have a weak event, but from the atmospheric perspective, we're actually seeing stronger signs of this La Nina. So basically, we have this flow chart when we decide whether it's La Nina conditions. First, we start with that Nino 3.4 SST region, and if that's in excess or less than minus 0.5 degrees C, we go to our next box. Do we think it's going to stay in that for the next several seasons? We did. When we issued this La Nina advisor, we said yes. What does the atmosphere look like? Well, we want to see those shifts in the Walker circulation, shifts in rainfall and pressure. And so, yes, we were able to say yes to all three of those things, and we declared the onset of La Nina conditions. This is the outlook. This is, again, issued 13th of February. And this is using the climate models and forecast systems that take in all that satellite and buoy information, feeds them into supercomputers, which are run every day to create the simulation, the starting conditions for our forecast models and enable us to create these ENSO outlooks. In blue are the chances of La Nina, again, in percent chance. And what you see is that we have just slightly less than a 60% chance of La Nina persisting in the February, March, April season. And then that drops to about 35% in March, April, May. And then ENSO neutral is the favored category going forward. There's a caveat to all this. The forecasts made this time of year are actually not as accurate. We know about this spring prediction barrier from NOAA research that has looked at this problem, and we realize that, yes, this time of year is when the forecast models are not as strong in predicting the upcoming El Nino La Nina. Usually, as we go into the rest of the year, that's when our skill increases and we become more confident in the potential upcoming state of El Nino La Nina. So right now, we have models, predictions being made, initialized in January and February. We see this big steep drop in statistical model skill and also even in our dynamical models. These are just different types of models that we use. As you see, when you initialize these models later in the season, these lines become closer to 1, meaning that you have more skill. So I do want to take a little bit of time aside and point out that this plot and these figures were part of the ENSO blog that was published yesterday morning. Yesterday afternoon, Tom DiLoberto and Rebecca Lindsay were let go. They were terminated. And as a scientist, it's really quite challenging to see this sort of behavior because, quite frankly, these are among the best NOAA has. I'm sorry to get emotional about it, but these are amazing, awesome scientists. And they have so much experience. Tom is the 4th most experienced person on our ENSO team in making ENSO forecasts. Rebecca is an amazing editor. I mean, people are always like, wow, why is your ENSO blog so good? It's Rebecca. Anyway, please keep them in your thoughts. Okay, let's shift gears and talk about the impacts potentially coming up here. So how does the tropics impact North America? Well, there's shifts in rainfall. And as you can see here, these shifts can also impact these cells, these overturning cells that occur north and south of the equator. So ultimately, like El Nino enhances convection, it energizes these cells through complicated dynamics like thermal wind balance that can strengthen the jet stream and impact North America. La Nina does the opposite, actually suppresses it. These cells anomalously are weaker, and we actually see the jet stream weaken in a certain place. So let's go back to the map view. This is showing pressure patterns, which, because of these geostrophic wind balances, are an indicator of where the jet stream is. So right now, El Nino, well, not right now, but in warm phase, El Nino means the jet stream shifts to the south and it strengthens, and that goes across North America. In La Nina, we actually see the opposite. It tends to shift to the north, and we actually see a weakening of the jet stream right in this region. All right, so it's weaker than it is typically during an El Nino. And so as a result of this northward shift, what we see over North America is wetter conditions. It tends to bring in more onshore flow from into the Pacific Northwest, and it affects storm tracks over the Ohio and Tennessee Valley. And in the south, we see drier than average conditions because the jet stream is shifted to the north. It also can affect temperature patterns, but for now, I'm actually going to, in the next couple of slides, focus on precipitation. And one thing I want to really highlight, especially with this audience, is that this is a schematic. So it's a very simplified version of what you would expect with La Nina. But there's a lot of variability about that. And so the pattern that you see from winter to winter will vary dramatically at times from this. It won't, you'll never see the perfect La Nina schematic pattern. But there's still value in knowing the state because in the net, we do see these tilts in the odds toward wetter and drier conditions. So this is the expected precipitation pattern during November, December, and January. I'm picking the season because I have the data through January 2025. And so we see drier than average precipitation across the southern tier, wetter to the north is expected from that jet stream shift. And here's what we see most recently. So this is updated through last month. And what we see so far this winter is we have these drier conditions in the southwest and also the southeast. But it's been a little different from expected over here in the southern plains and parts of Oklahoma, Texas, Louisiana, where it's been wetter. You can see Northern California has been wetter too, which is a little different from the typical pattern. And even in parts in the Pacific Northwest have been a little drier than expected. But keep in mind, this is a weak La Nina. So weaker La Ninas mean there's less of a punch being thrown onto the atmosphere. And so we tend to see a little bit more in terms of deviations during a weaker event. In fact, I can quantify this. I can take these two maps together and assign it a number. I'm going to give it a match score. This match score will tell us how similar these two maps are. And for November, December, January, the one we recently have, the match score is around -0.1. Okay, what does that mean? That doesn't have a lot of value, I realize, by itself. So I'm going to show this scatter plot. And what is showing is the 24-25 winter, that -0.1 value. And on the y-axis here, basically is showing the intensity of that match score. So right now we're seeing a weekly negative match score. But if you travel down this y-axis here, basically these are larger match scores. These mean that you would expect to see a better resemblance between the typical La Nina pattern and what actually occurred. This red line's the opposite. You can see here that as you get stronger, that means the match score is more similar to the typical El Nino pattern. All right. And remember, I was saying the schematic is just a simplification of what we see. It's certainly very simplified because as you see here for weak La Ninas, and on the x-axis is the intensity of the La Nina. The smaller values are weaker La Ninas, bigger values are stronger La Ninas. And on the right, weaker values here are weaker El Ninos, and then to the right are the stronger El Ninos. And the most interesting thing you see is that these dots are aligned in this diagonal fashion, which basically means that for El Nino, especially the stronger ones, you tend to get better resemblance between the precipitation pattern and the typical or expected El Nino pattern. And the opposite is true for La Nina. So if we had a stronger La Nina, we might be down here and really see a better match score between what we're seeing now in this winter and what the expected La Nina pattern. But it's because we're seeing a weaker La Nina, our match score isn't quite as good. But keep in mind, there's a lot of variability about that. In fact, there's some winters, as I'm going to show coming up here. And I'm just going to point out each of these dots is a different winter. And so this is the most recent winter. And now I'm going to point out some of these other dots up here, down here, like 2008-09. This is a very strong match score between the expected La Nina pattern and what actually happened. But even there, you can see some variability. Pacific Northwest is different here in 2008-09, but overall, there's a lot of similarity. But you can also get really bad match scores. So this is 2022-23, which actually looked a little bit more similar to El Nino. We saw the exact opposite in the West Coast. You can see it's wet for here, wetter here. And that was not expected with a La Nina. But this is what you can expect. There is this variability. There are surprises. But in general, you can hedge. And if we couldn't hedge, then we would just see all the scatter flying about here. And there would be no alignment in the diagonal that we see here. So we know this ENSO information is meaningful from analysis like this. This is what's upcoming. I was looking back at what recently happened. This is March, May 2025 CPC outlook and seasonal precipitation and temperature. And again, these are probabilities. You can't bet the farm on this. This is slight lean for below for Florida, and then of course below average chances here in the southern tier going up into the Mountain West. And then above average chances in the Ohio, Tennessee Valley, and also the Pacific Northwest. Temperature, still expecting below average temperatures in the Northwest, and then a tilt toward above average temperatures for the southern tier and also the East Coast. So that brings me to the end of this presentation. We are in La Nina conditions. We are in advisory. Temperatures in the tropical Pacific reflect a weak La Nina. Interestingly, the atmosphere has been stronger than the ocean. Over the contiguous United States, we have seen some of the expected La Nina signs and precipitation anomalies, but other features, of course, have been inconsistent. And even as this weak La Nina dissipates and we go to ENSO neutral this spring, keep in mind that these La Nina impacts can still persist. There is some lagging in the atmosphere, and we still see these signs even in the tropical Pacific atmosphere that this La Nina has some punch. So we are hedging in favor of this persistence as we get into the spring. And with that, I'll go ahead and wrap things up. Thank you so much.
Okay, thank you very much, Michelle. Fascinating insight into how NOAA does its operational predictions. Thank you. Maybe we'll take one quick question, and that's sort of the age-old question, chicken and egg. Are the sea surface temperature anomalies the cause of the oscillation, or are they a symptom of the oscillation?
I love that you use the expression chicken and egg, and that is why we exist. Because it is not totally obvious where it starts. Is it the chicken or is it the egg? Is it the ocean that is pushing the tropical atmosphere along, or is the tropical atmosphere pushing the ocean along? And sometimes it's one, and sometimes it's the other. There are times, especially when we go from El Nino to La Nina transitions, where it's probably a lot of the ocean pushing the atmosphere along. And that's because of some special dynamics inherent to that situation. But there are other times where we see atmospheric, the atmospheric state over the tropical Pacific changing, and then that pushes the ocean toward an El Nino or La Nina. So it's really both, and it depends. Great question.
Okay, super. Yeah, thanks, Rick, for that question. Okay, let's move on to Nat. Just as Michelle talked about all that we know, Nat's going to throw some interesting spin on that, and especially as we look at the changing climate, what does that mean, Nat, for future projections of our winter forecasts? So without further ado, bring you Nat.
Great. Thank you so much, Brad. And thank you, Michelle, for a great lead into my talk. Okay. So in my talk, I'm going to cover this topic of what else shapes our winter climate and will ENSO's influence change in a warming world. And so what I'm going to try to do is address these three questions, and because of limited time, I'm going to do so somewhat hastily, but hopefully get something out of each one of these three important questions. So first of all, the question, we have an El Nino or La Nina, and we have these certain expectations, and sometimes we don't see those expectations, as Michelle just explained in her talk. So the first question, why was it El Nino or La Nina in my backyard? So what other factors influence our winter climate? And then the second question, how has ENSO been changing over the past century? So can we detect significant changes from our observational record? And finally, are ENSO and its impacts expected to change in the future? And specifically, will increasing greenhouse gases change ENSO? Okay, so for that first question, I'd want to take us back to this La Nina in the winter of 2022-23, as Michelle briefly mentioned. So this was a very classic La Nina pattern in the tropical Pacific Ocean. This was actually the third winter of a 3-year La Nina. And you look at the seasonal precipitation outlook from NOAA CPC, it was a classical canonical La Nina pattern, enhanced probability below average precipitation in the southern US and above average over the north. So this is what we expected. And then what did we get? And maybe you may remember this, but we had a winter from basically late December, especially late December through mid-January, where California just got pummeled by atmospheric rivers. So very wet conditions over California, which we don't typically expect during La Nina. So what went wrong with the forecast? Did we miss some signal from the sea surface temperatures? And then back in February 2023, I wrote a post for the ENSO blog asking, did La Nina drench the Southwest United States in the early winter of 2022-23? And for this, what I did is I analyzed different simulations of La Nina winters in a climate model, GFDL SPEAR model, which had 30 different ensemble members. So really sampling the chaotic variability from the atmosphere that we can get for an individual La Nina. And I did find different ensemble members that produce wet conditions in California during La Nina. So up on the top right, you can see the difference between the wet and the dry La Nina winters. And we could get some very wet La Nina winters over the Western US in the climate models. Then I tried to see if there was a clear sea surface temperature signal for those wet La Ninas. Maybe there's some kind of flavor of La Nina that was producing the wet conditions. But basically, I found no clear sea surface temperature signal. So that meant that these differences were just due to chaotic weather rather than a flavor of La Nina. So with the same La Nina sea surface temperature anomalies, sometimes you get wet conditions and sometimes you get dry conditions. Okay, so that's still not a very satisfying answer. So what really happened, and could we have predicted it? Well, another major influence on the US winter climate is the so-called Madden-Julian oscillation, or MJO. So this is also a tropical, like ENSO, a tropical pattern that's characterized by anomalous rainfall, but this is more subseasonally evolving. So this is kind of the rainfall pattern. You have enhanced rainfall in the greens and blues, suppressed rainfall in the browns, and this pattern really travels across the entire tropical belt over a time scale of about 30 to 70 days. And there was evidence of this paper led by Siegfried Schubert, suggesting that the MJO did play an important role for this California flooding. So they're suggesting that this outflow from the MJO in the Indian Ocean, it initiated this short wave that traveled along the South Asian jet, eventually initiating another vorticity forcing of this positive PNA pattern, which had low pressure over the North Pacific, leading to wet conditions over California that really contrasted the typical La Nina influence that we expect. And so was this something that was predictable? So this is another plot from their study showing the prediction skill of the upper tropospheric pattern from the late December through mid-January. And this y-axis here is a measure of forecast skill. And what I want to point out is if you look at forecasts that were initialized on December 17th, you can see that the skill drops off very quickly. But whereas you look in the red here, these are forecasts initialized 5 days later, and all of a sudden the forecasts do much better, and they actually do quite well all the way to middle of January. So something changed in the initial conditions between the 17th of December and the 22nd of December. And they actually got some very good subseasonal skills. So the key point here is that this prolonged California flooding had reasonably good subseasonal skill, but may not have been predictable on these seasonal timescales. And this is also echoed in this De Florio et al. Paper in 2024. So just to zoom out a little bit, so what other factors can influence or shape our US winter climate? So I mentioned the MJO. Another factor, stratospheric polar vortex variability, and often, we focus a lot on these so-called sudden stratospheric warmings. And I also recommend checking out the climate.gov polar vortex blog for all the latest information on the winter polar vortex. Another factor, just chaotic extratropical weather variability that impacts the large-scale atmospheric circulation patterns, so-called teleconnection patterns like the PNA, or Pacific North American pattern, North Pacific Oscillation or West Pacific pattern, and the North Atlantic Oscillation or NAO patterns. And the patterns like the PNA can be forced by the tropics through ENSO, but they can also exist independently of this tropical forcing. So just chaotic weather. Other factors, different flavors of ENSO. So there's a lot of research on, on whether, on like Central Pacific versus Eastern Pacific El Nino. So we may have different impacts from the different types of ENSO flavor. Also decadal ocean variability, like so-called interdecadal Pacific Oscillation or Pacific Decadal Oscillation. The quasi-biennial oscillation. So these are variations in the tropical stratospheric winds with a approximately 2-year time scale that may have influence. Cryosphere variability, such as Arctic sea ice changes. And radiative forcing, major volcanic eruptions, anthropogenic aerosols, and especially our increasing greenhouse gases. But rather than go into all the details of these different factors, I'd like to just break them down into 3 different categories. So these first 3 are generally predictable only on these subseasonal and shorter timescales. So like what I just described about the MJO. So it means that even though they can shape our winter climate, they're generally not going to be reflected in our seasonal outlooks with the longer lead times. You won't be able to, really anticipate their influence, say in October or September. Then the next 4 are potentially predictable on the seasonal timescale, but they really have an uncertain influence. So maybe their relationships are based on limited observations. So we don't have enough observations to really find a robust influence. And oftentimes when we have limited observations, we want to we turn to our models, our climate models, to kind of supplement and give us some additional evidence. But in these cases, we often find weak or inconsistent model responses. And also underpinning all this, we need a theory behind the reason why we expect such an influence. And then oftentimes for these, our theory is incomplete. And then the last one, the radiative forcing, these are important for seasonal outlooks, and especially when you look at temperature trends as a result of our increasing greenhouse gases. But given the, the uncertainties, given the limitations of these first 2 categories, it helps to explain why when we look at our seasonal winter outlooks, they tend to be dominated by the canonical ENSO signal and plus the trend, especially for temperature. So it doesn't mean that we still need to do some more research into these other factors, see if there's something that's missing in our theory, in our models, and maybe there are some more signals that we can tease out. But for now, really the dominant signal is going to be from our canonical ENSO signal. Okay, so has ENSO been changing in recent decades? And first, I want to mention why this is a challenging question to answer. And this is, I think, brought out by a study led by Andrew Wittenberg in 2009. This is based on a climate model that was run for 2,000 years with radiative forcing, including greenhouse gases, held fixed. And then here I'm showing time series of the ENSO variability in terms of tropical Pacific sea surface temperatures over all 2,000 years in that simulation. And what I want to point out is there are particular epochs, like for example, this M5 here, where you see the ENSO variability is very weak over this 40-year period. On the other hand, you can pick out other epochs like this one, M7 here, which shows 40 years of very strong and regular ENSO variability. And so you're tempted to say, well, something must have changed between M5 and M7. So maybe the greenhouse gases increased, or maybe there were more volcanic eruptions, or the solar cycle was different. But no, actually, the same rate of forcing in these two different epochs, it's just chaotic climate variability that's responsible. And so you can imagine in observations, we might have a 40-year period where we have weak ENSO variability like this, or in a 40-year period where we have strong variability, and there really is no external forcing response. So the key point is here is that these variations in ENSO variability between multi-decadal epochs are purely random in this model and not due to changes in greenhouse gases. So despite these observational limitations, there are some evidence of changes. So if you look at the, here I'm looking at the observed record of Niño 3.4 sea surface temperatures, and you can see some evidence of more extreme swings between El Nino and La Nina after 1960. So before 1960, not as many extreme El Ninos and La Ninas. After 1960, we are seeing some more of these extreme El Nino and extreme La Ninas. But again, observations are not sufficient to draw any firm conclusions because of just how chaotic the climate system is. But this does have some broad climate model support that greenhouse gas warming may have contributed. So I won't say it's a slam dunk, but there is evidence in support of this. Another interesting change that we've been seeing is if you look at the La Ninas that we've had, like what we have this year, it seems like they're more frequently occurring as multi-year La Niñas, so persisting for 2 or 3 winters. So this is the Oceanic Nino Index table you can find on the CPC website. And looking at the recent La Niñas, you can see most of them have lasted, multiple years. The most recent one lasted for 3 winters in a row. And this was actually the study led by Dr. Ben Wang in 2023, actually pointing out that 8 of the 10 multi-year La Niñas over the past century have occurred after 1970. So it does suggest that there's a trend toward more frequent multi-year La Niñas. And they argue that this recent increase in the zonal sea surface temperature gradient between the central and western equatorial Pacific may have contributed to this trend. So if you look at the trends of the sea surface temperatures, you could see it's been warming more in the western Pacific than the eastern Pacific. And also note that this is not something that our climate models tend to reproduce. Climate models tend to produce more warming in the eastern equatorial Pacific. So it's not clear whether this is a trend that's going to persist, but it may have affected what has occurred in recent observations. And then also an important problem is understanding how the warmth outside of the eastern Pacific may be affecting ENSO impacts. So over here, I'm showing the same sea surface temperature animation that Michelle showed earlier, showing the cooling over the eastern equatorial Pacific. But you can also notice that there's some very warm conditions around this region, particularly in the western Pacific. And if you look at the global sea surface temperature over the last few years, you may be aware that we've seen some record-shattering global sea surface temperature anomalies. So showing the lines in 2023, 2024, and early 2025, really much higher than most of the previous years that we've seen. So how might this be affecting how we should monitor ENSO and what the impacts of ENSO may be? Well, fortunately, there's potentially a very simple ENSO monitoring solution, and Michelle has been instrumental in some of the research that has put this idea forward, but simply just defining a relative Niño 3.4 index, which is basically just the traditional Niño 3.4 index and subtracting the tropical mean sea surface temperature anomaly. So it's looking at the Niño 3.4 index sea surface temperatures relative to the rest of the tropics. And there's some good physical basis for why we would do this based on the weak temperature gradients in the free troposphere and the tropics. I won't go into that, but basically because the oceans have been warming so much, we've been seeing a growing difference between the traditional Niño 3.4 index and the relative Niño 3.4 index. So particularly over the last year or so, we've seen differences around 0.5 degrees Celsius, where the traditional index is much warmer than this relative index. So what can that mean for impacts on the U.S.? So back in early December, I wrote another blog post. So adding with this question: can a little La Nina pack a big precipitation punch? And then, so what I'm showing right here, this is the precipitation forecast for this winter from a bunch of dynamical models that form the North American Multi-Model Ensemble, or NMME. And so what you can see is a pretty classic La Nina precipitation pattern, which is not surprising because we have La Nina. But what was surprising, at least to me, was that this pattern is actually a pretty strong forecast pattern. In fact, it was this, its 6th strongest precipitation forecast out of all 34 forecasts since 1991, despite being only the 18th strongest ENSO forecast using the traditional Niño 3.4 index. So, what's going on here? So it turns out if you look at the model forecast using the relative Niño 3.4 index instead of the traditional index, this winter's La Nina was much stronger. And that would seem to be consistent with what Michelle was talking about. The tropical atmosphere has been showing, a stronger response than you would expect from a weak La Nina, at least by the traditional metrics. And importantly, the dynamical model's precipitation forecast more closely match the stronger relative Niño 3.4 index than the weaker traditional index. So here again on the left, I'm showing the forecast from the NMME models. And on the right here, this is the pattern expected based on the relationships with the relative Niño 3.4 index. And you can see it's a very good match. Whereas if you use the traditional index in the middle, you get a weaker pattern. So one that is more consistent with the weaker La Nina. So it does suggest that that considering the relative temperatures in the eastern equatorial Pacific relative to the rest of the tropics can be important for impacts. So are these impacts expected to change in the future? Well, I mentioned, that we've seen some bigger swings between big El Nino and La Nina in recent decades, and climate models generally suggest that this increasing sea surface sea surface temperature variability will increase in a warming world. So this is looking at projected changes in the Niño 3.4 index in various climate models, looking at the 21st century in purple, 20th century in green. And you can see in most of the cases, the purple bars are bigger than the green bars. So that indicating more ENSO variability. There's even more agreement on these increases of extreme El Nino in terms of tropical Pacific rainfall rather than conventional sea surface temperature metrics. So if you define extreme El Nino based on the tropical Pacific rainfall, then we do see even more agreement that we would see more extreme El Ninos. And one reason you might do that is because the global impacts of El Nino occur through the tropical convection exciting these large scale patterns. But I would note some caveats. Again, we have large random internal variability. So even if greenhouse gas warming is nudging ENSO one direction, we only have one reality, and in that one reality, the chaotic nature of the climate system can push us in the other direction. We also know that there are still persistent climate model biases and disagreements in compensating changes, so that will limit our confidence in these SST changes. And finally, as I noted briefly before, there's a mismatch between the observed and simulated tropical Pacific climate trends. And so these changes in the tropical Pacific mean state are important for how ENSO is going to change. So this is something that we really, I think is important for the scientific community to reconcile. Nonetheless, some models project a strengthening of these ENSO impacts under global warming. So this is a study I published a few years ago, looking at the precipitation and the temperature patterns associated with El Nino basically the historical climate on the left. And in the middle, this is the changes in 2011 to 2040. And then on the right, these are the changes by the end of the 21st century. And you can see the change patterns match the historical patterns pretty well. So that's suggesting that the pattern of rainfall and temperature are projected to strengthen in the future. And they do see some changes in the pattern by the end of the 21st century, though it's not clear how robust those are. So if we zoom in on the US, this is a study that was just recently accepted, on which I was a minor contributor. But it's suggesting that we also expect a projected increase in the ENSO-related precipitation signal. So this is looking at how much the precipitation is related to El Nino or La Nina in the historical climate on the left, future climate on the right. And you can see there's a stronger connection between ENSO and precipitation in the future climate, in this climate model, over certain regions like the Western US as well as the Southeast. And this is a measure on the bottom is a measure of the so-called signal to noise ratio. So how much the signal related to all that other chaotic weather variability that I talked about. And we see an increase in the signal to noise ratio over parts of the Southwest, Northwest, and Southeast. And so now that's could be good news because it would imply that we would get better winter seasonal precipitation predictions in the future, assuming that our predictions of ENSO itself are held constant. But it also means we may see more ENSO-related extremes. So this is also looking at these two periods in the climate model, but looking how El Nino-related wet extremes change and how La Nina-related dry extremes change. So interestingly, we see a big increase in El Nino-related wet extremes over the eastern US. And this is not a region that, parts of the Northeast, it's not even a region that's closely associated with El Nino-related precipitation, but in the extremes, we do see big increases. Whereas for La Nina, it's more centered in the Southwest, so bigger La Nina-related droughts projected in the future in this model. And this is kind of a schematic showing, just summarizing these big changes, where we see the big, more extreme wet conditions in the from El Nino in the Northeast and Southeast, more dry for La Nina. So note this is only from one climate model, although there's some general agreement in the general pattern among different models, but it does suggest that there's a potential for increasing in ENSO-related extremes in the future. Okay, so here are my key takeaways. There are many factors that can shape the US climate in any given winter, but ENSO provides the most reliable, seasonally predictable signal. And ENSO has undergone some notable changes over the past century, including some more extreme swings and more frequent multi-year La Niñas, but it's not clear how much is natural and how much could be a response to anthropogenic forcing. And then finally, climate models generally project increases in ENSO amplitude and winter impacts over the US, though more research is needed to be fully confident in these projections. So thanks so much.
Okay, thank you, Nat. Intriguing, fascinating atmospheric mysteries. I have a question for you, is that as far as you talk about the potential in the last couple images there of more variability, more extreme events, and then you looked at the especially La Nina with drought across the desert Southwest. Are those singular years, or am I wrong? And we saw the one analysis that showed more multi-year events. And is there, stumbling a little bit my question, but is there an expectation that not only they'll be more extreme, but they will gradually transition over to more multi-year events so that we could have more impactful droughts that extend over 2 or 3 years? Or would you interpret or stay back to 1 year at a time analysis?
Yeah, that's a great question. So that analysis was just looking at the 1 year at a time. So for a given winter, more likely get extreme. But you raise a good point that also what's going to be important for impacts is whether or not we do have more multi-year La Nina. So I think there have been some suggestion that we may see more multi-year La Ninas, although I don't think the confidence in that is that high at this moment. And I mentioned, the study that looked at it in the observational record. We have seen more multi-year La Ninas, but again, that may be contingent on the particular pattern of warming and cooling that we've seen in the Eastern Equatorial Pacific in observations, which, as I mentioned, does not agree well with what's in climate models. So to have confidence in whether that's going to continue in the future, I think we have to really reconcile these diverging trends in the tropical Pacific.
Mm-hmm. You obviously the focus of this hour has been North America and our winter season. There's a global thumbprint of ENSO in different things. Have you been able to look at some other areas and other seasons that might add additional insights into sort of what the overall global circulation, how it might be responding? Or, it all starts with, I think, 100 and some odd years ago with Sir Gilbert Walker in India looking at the failure of the monsoon. How are all those circulations, and do you have any thoughts on that?
Yeah, so certainly I haven't looked closely, though I know others have. I know there are changes beyond the winter season, including changes in projected changes in the decay and the onset. I know, for example, that one of the other projected changes is a more closer connection between ENSO and the NAO. And so that would have implications for climate over Eurasia. So I know others have looked more closely at some of these other global changes and global impacts.
Okay.
There was actually a talk at AGU in December by some scientists who did look at the global pattern. And remember how Nat was talking about how you get this strengthening potentially over time. What that could also translate to is just more predictability and a stronger pattern across the globe. And there was some evidence of that, but that's unpublished work. And it's something I know scientists are looking closely at.
Okay, we have 1 minute. We have one more question. It's a really fascinating question. I wish we had more time. As the oceans overall gradually warm, are we reaching an upper threshold to the point where we may not have La Nina anymore, or the impact of turning the convection on and off may no longer be there? And answer that in 35 seconds. No.
I would say we haven't seen any evidence of that. So it also depends on, again, how you define your baseline climatology to define your Niño 3.4 anomalies. But so far in the projections, we see that there's still, variability about a baseline, which is, we do see warming, but there's still fluctuations
There's
about
still that
baseline.
yeah.
So, yeah.
Okay, super. Well, I want to take this moment before Gideon rejoins here and just thank both of you for taking the time today and sharing your expertise with the audience, and fascinating presentations, and couldn't express our appreciation more. So thank you both.
Thank
Now I'll
you.
hand it
Thank
to
you for this
Gideon.
opportunity.
Yeah, thank you. Appreciate it.
Well, yes, Michelle, Nat, and Brad, thank you so much for bringing that to our audience. It's been incredibly illuminating, and I learned a lot. So thank you, and I think the audience appreciates that very much as well. And yes, this brings us to our Riding Tropical Winds and Waves, How ENSO Shapes Our Winter Forecast webinar to a close. But audience, please stay tuned, because coming up is the Getting the Most from Your Home Weather Station Gemposium webinar. It's coming up at 1:15 p.m. Eastern Time. So we'll see you there. Take care, everybody. See you in a bit.